When three industry leaders unite, they trigger a cosmocollitic event that shatters the boundaries of learning. The result is a dimension beyond that which is known to the technician. It is the middle ground between theory and practice. It lies at the summit of our knowledge, in the spark of our imagination. Step into the third dimension to see the unseen. You are now entering, visualizing HVAC Excellence.
This is HVAC Visualized. Welcome back to another episode of Visualizing HVAC Excellence. Last week, we wrapped up our electrical fundamental guided pathway by using schematics as a roadmap for comparing what should happen with what actually was happening. Today, we begin a new guided pathway and bring the same diagnostic mindset back to the refrigeration system. Before we diagnose abnormal operation, we first have to understand normal operation under the conditions the system is actually operating in. Helping us bridge that gap is none other than my good friend, Ty Branaman, CMHE, founder of Love to HVAC. Ty, welcome to the show.
Thanks, man. It's good to have you. Good to see you again. It's been a while.
Likewise. So I'm excited to have you help us kick off our refrigeration diagnostic pathway. Ty, I'm joining from Southern California. Where are you tuning in from today?
Hot and humid Florida.
Hot and humid Florida. Yeah, you moved away from Texas, so you went to go join that hot and humid Florida weather, huh?
Yeah, it wasn't that long ago. We were living in Las Vegas, so it was hot and dry. Then it was a mixture of hot and humid and dry, and then now we're just hot and humid. So keep it moving.
Yeah, wonderful. So, and everyone watching, please share with us where you're tuning in from today. Today's webcast is brought to you by System Performance, Maximizing Energy Efficiency in Heating and Cooling, available from the ESCO Institute. Visual 3D Academy is proud to have the continued support of ESCO Institute and Fieldpiece Instruments as we work to make HVACR education more visible, practical, and accessible. See it, learn it, apply it. So, Ty, before we start looking at pressures and temperatures of the refrigeration system, tell us a little about your pathway in HVACR and what has shaped the way you teach refrigeration diagnostics.
Well, it's still an ongoing path because you have to keep learning constantly all the time. And there's never a point where you're like, oh, I have this. Even things that you think you have down, to revisit them again, you unlock new levels of that. And then when you're trying to teach somebody else, it's forever. You can have something that works great for years, and now you have a new student and they're like, I don't get it that way. And now you have to think of another way of explaining it. So the more things we have, the more tools that we have access to be able to explain things in a variety of ways, the better we're going to be. And also for your students that already got it that first way, having them experience or see something in another way and another way and another way gives you that broad viewpoint all the way around, and it makes everybody on a better level, a new level, with deeper understanding of the subject. And so I'm all for multiple ways of somebody learning something.
Absolutely. So, speaking of learning, and then of course challenging what you have learned, we hold the Certified Master HVAC Educator, or CMHE, credential from HVAC Excellence. For those watching who may not be familiar with it, briefly explain CMHE and what it represents to you.
Well, for me, it was about myself, my own path of learning, and I struggle with tests. Have test anxiety. I struggle with capital and lowercase, getting numbers and words backwards. So when I started that journey, I said, "Heck, I wanna get CMHE," and it took several years before I got that. And I would go in taking a test, saying, "Hey, I'm gonna fail this test. That's okay. I want to see what it's about." And so as soon as the test was done, I would write down as many things I could think about, and I'm looking for like these little pieces of information, but then I would learn like massive amounts of information searching for these little obscure things. And you could say, oh, well, I don't need that in practicality. That's an easy way to blow it off. But the bigger thing is finding information you're looking for is a super fun challenge, because now you realize there's something you don't know, and then the search to find it is incredible, and then how much you learn on that pathway getting there is the real win. And so I enjoy taking tests for that purpose alone. And hey, it doesn't matter if you failed the first time. It's how many times did you keep trying and what did you learn on the way? It's that path that makes it so good.
Absolutely. And that brings me to a good point here. And just so everyone's clear, ESCO and HVAC Excellence don't just offer 608. By the way, there's a new test coming, and you just learned about that, Ty, apparently. But there's a new test coming. I can't say too much about it yet. More to come. But ESCO at HVAC Excellence does offer more than 608 alone, and between CSME to CMHE pathway, as well as your employment ready and your professional level certifications. You don't know what you don't know until you don't know what you don't know. So, absolutely. So, anyway, that brings us directly in today's episode. Diagnostic foundations. No normal before you diagnose abnormal. We are not starting with an undercharged or overcharged or another fault condition. We are starting with a normally operating refrigeration system and asking what the system should be doing under those conditions. The goal is to establish a baseline we carry through the rest of the guided pathway, expected versus actual pressure, temperature, superheat, subcooling, and overall system performance from approach to DDT to CTOA, etc. And just as important, we want to make clear that normal is not one universal set of pressures. I love one of your videos, Ty. The pressures. Throw the paper away, right? under a load, outdoor ambient, equipment design, and metering device all affect what we should see as normal. So, Ty, as a technician decides whether any pressures or temperatures specifically are normal, what operating conditions do they need to truly understand first?
Well, airflow. We got to have proper airflow. Even if you don't have the tools to measure it, just some visual aids like making sure you have a clean filter, clean coil
Mhm.
outside, that it's not clogged up, dirty. Just making sure we have airflow. If we don't have airflow, then none of those other numbers are going to matter. And then the best place I've seen normal was on a washing machine, but never else you don't really see normal.
Well, the normal cycle, right? On the wash machine, a little knob, but yeah. So ABC, right? Air before charge, as we all know your ABCs. So absolutely. And then, of course, if we get the airflow right or get the airflow within designed conditions, we can tune up or tune into what is normal on the refrigeration side. Absolutely.
Absolutely correct. Yep.
So, all right. Well, looking at looking at the system that is operating properly, walk us through the checkpoints you want the learner to pay attention to, and what those readings begin to tell us about the system entirely as a whole. So, not the washing machine with normal cycle.
Well, I first want to know what kind of metering device do I have, because that tells
Yeah.
me the next steps entirely. So, do I have a fixed orifice capillary tube? Do I have a TXV or electronic expansion valve? Because that's
Mhm.
going to make my next steps. So, TXV is the easier one because it doesn't have to work for us. So, we need to know our targets. If I'm driving and I'm saying, "Hey, you're going 55," is that good, or is that bad? Well, we need something to compare it to. So, when we're starting, let's find a metering device. What metering device do we have? And then we can start looking at our target superheat and our target subcoolings. And those are going to be different depending on that metering device. So, first up, hey, what metering device do we have to know how that device works? Before we get to that next step of where do we go from there? Hey, what metering device do we have? What kind of controls do we have on that refrigeration cycle?
Absolutely. So you make a good point about superheat and subcool. We have two sides of the system, a high side and a low side, and the two components that regulate that is our metering device and our compressor. So let's talk about superheat and subcool as a foundation level. What do you want the learner to understand about what each one tells us before they begin using those numbers diagnostically? So, hey, 400 psi is roughly expected, at said temperature or at said, CTOA, et cetera, or the DDT, design temperature difference. Tell us a little bit about that. Hey, that is way out of whack. Say you have 500 psi on the high side and 20 psi on the low side. That's a problem.
Right. I
So,
start with superheat and subcooling. Where is my refrigerant? I want to see where the refrigerant's at. Now, the other numbers are going to be important, help us
mhm.
dial in what's going on, but I like to visually be some way of seeing that. Now, there's lots of ways we can do it, drawing stuff. I like to use water, for example. Behind me, I have my water jug over there with a little bit of red liquid in it. So that represents my subcooled liquid. So in the condenser, especially if we have a TXV, we want to know that we have enough subcool to feed that. And what's normal? Well, we look at the manufacturer data and see what's their target subcooling. Had one this week that was 5, and on the same day I had another one that was 12 degrees of subcooling. So normal is going to depend on that manufacturer. They decide what my subcooling is, but everybody's talking about, oh well, this it's just this number, and you got to make sure these numbers match. So I like to have some way of making it visual. That's why I love you guys, because you're making stuff visual for people, and that's incredible. So just like I'm using a jug of water here to see how much liquid refrigerant stacked in the condenser. So if I have enough subcooled liquid in my condenser compared to what the manufacturer wants for subcooling, hey, I know I have the right amount of refrigerant in the condenser. Now, if
Yeah.
I'm have too much refrigerant or not enough refrigerant in the condenser, that's just one part. I don't judge everything on just that one number. And what's cool about subcooling and superheat is it goes over all the other numbers, all the other refrigerants. It breaks it right down to superheat and subcooling. The liquid saturated temperature, where it's changing state, pressure
Mhm.
converted temperature, minus the actual liquid line temperature, which should always be lower. So the
Should be.
higher number, saturated temperature, minus the lower number, that's your subcooling. It tells you how much refrigerant is stacked in the condenser.
Yeah.
What's normal? Well, what does the manufacturer say is for normal for that metering
So
device?
yeah. If we pull, Dirk's behind the scenery, but if we pull that stacked refrigerant up in that to the three parts of that condenser coil, Dirk, you had it up there. It was a video. I don't know if it was which one it was, but it's exactly what Ty is explaining right there. You got your superheated vapor, you got your saturated, you got your subcooled liquid, and those can all change depending on conditions, and not just ambient conditions, not just conditions, poor airflow, etc. You could have poor airflow outside, but also the conditions of the refrigerant, right? How much is in the system. So absolutely. But yeah. All right. So let's kind of get a you mentioned about visualizing this, Ty, and let's pull up our pH chart, pressure enthalpy chart, and take a look at it. When I first started learning pressure enthalpy, and we're not going to make this a pressure enthalpy course or topic today, but be able to visualize it. And that's what we're trying to do, is bring this to understanding. It's like, hey, what happens when X? Or hey, what is normal? And again, no, not the normal cycle on your washing machine. But as we pull this up, we have our envelope here, and walk us through what's going on as we change the outdoor ambient, change the SEER rating, change the airflow, etc.
Yeah, so as you change your outdoor temperature and your SEER rating is all going to affect where that saturation is. And what's cool about having the saturation, doesn't matter what your pressures are. If you convert that to a saturation temperature, you have a much more regular number to go with. And then that's the number I really want to look at. I want to see where that refrigerant's changing state. So as the outdoor temperature goes up, yeah, your outdoor pressure is going to go up. And do I need to memorize all 200 and something different refrigerants? No, I look at that saturated temperature. So depending on the C rating of the system, is going to depend on how much warmer that saturation is going to take place at. So if it's a high SEER system, my saturated temperature, the temperature at which it changed states, the majority of my condensing coil is going to be a lot closer to the ambient air temperature, because they've built the system to be more efficient. So they're using better forms of heat transfer, whether it's microchannel, whether it's more tube and fins, whether it's a different style tube and fins, whether it's moving more airflow. They've done something in there to make sure that they've gotten that condensing temperature closer to the air temperature and still remove all of the heat that it needs to remove to make it change state. Now, in the older systems, like back in my day, back in the 80s, we those systems, that was before me, those systems had a very high temperature difference. So you'd see
Yes.
35. And so 35, the saturated temperature is 35 degrees higher than the air temperature. So we had a small amount of space so to make all that saturation take place, which means we'd have a much higher condensing temperature to make that heat reject in a very short space. And now that we have more efficient ways of transferring heat, I can get that head pressure down. More importantly, that saturated temperature down, takes pressure off of the compressor, lower compression ratio.
Right.
And then now we can have it sometimes as low as 10 degrees. So the saturated temperature can be 10 degrees warmer than the air temperature. So it's amazing what they can do. Now, typically you don't see them that low. Usually 15 is a more reasonable number. But
Oh yeah.
getting that saturated temperature down closer to the air temperature is an important factor. So now we can look at that number and be like, hey, I got a high efficiency system. But the difference between the air temperature coming in and my saturated temperature is at 35.
They got a
why
problem.
is it so high? Like, what's going on? And there's a lot of things that can cause that. And we can go over the whole diagnosis, but the first thing is like, hey, that's not
Normal.
normal. We need to see what's going on. So the age of the equipment, luckily there's not a lot of the 80s systems out there, which I still like. I have a jug of R22. I still work in some of those that are out there. It's just understanding, hey, what was normal back then is a lot different than what's normal now. So understanding the SEER rating, the efficiency of that system. And you can have two things working together. If I flood my condensing coil with too much liquid refrigerant, I have way too much refrigerant than I need, or a restriction, anything else, I start backing too much subcooled liquid into that condenser, I flood the condenser with liquid. Now I'm back to making that saturation take place in a very short area, which you would see that in your condensing temperature over ambient, your condensing temperature rise, or your condenser TD, as some people call it. So that way
Yeah.
you can see, hey, I got a way too much subcooling outside, and my condensing temperature over ambient is way higher than what
Crazy.
normal is. I know I have two things telling me something's wrong out here.
Yeah. Well, a few things you were speaking there of C2A and a larger SEER or a higher SEER, more efficiency equipment. Of course, it's going to grow too because we have to be more efficient, and we can capture or make a better heat transfer, similar to a 90% furnace. Right? We can get more efficiency out of it. Right? We can do more. But one thing that I know, and and that took me a while to understand this, is that a higher efficiency piece of equipment, 20 SEER plus, etc., is that approach is like so close to ambient that there's hardly anything there. And sometimes subcool will be so close to it's hardly there. And it's because that equipment is so efficient. Is that something you recognize too in your in
Oh yeah,
in your
so
career? Yeah.
our liquid line temperature, the lowest we could possibly get it down to is the ambient temperature. The only way, if you have your liquid line temperature lower than the ambient temperature, then you have something acting as a restriction before that point, and it's actually, but there's a metering device in there that a filter dryer, something turns into being a metering device. So we see, hey, if our liquid line temperature is below the ambient, there's something else going wrong or out of calibration on your instruments, because it can
Yeah.
just only get down as low as the outdoor temperature. So understanding what would normal be, it's the best case scenario. I can only get to this point. Hey, I'm beyond that. Something else is going wrong. Like let's look at that. That's not normal. And so we'd go into looking at that. So if
Yeah.
we have for example, a high efficiency system, maybe it's only 10 degrees above ambient. That means the best subcooling I could ever possibly have on any day would be a 10 degrees of subcooling, because I only get that liquid line down 10 degrees, right? That's or equal to the ambient. So that's why some of these systems, a higher efficiency system, may only call for 5 degrees of subcooling. They're looking for a 10 degrees saturated temperature above ambient. So
Right.
if the liquid line even got, the best we could get any hopeful day is ambient, there's not enough room to have that balance between subcooling. So you'll see some manufacturers be like, hey, yeah, we only want 5 degrees of subcooling. That's what we're going to call normal for our equipment. And sometimes it's other things such as how much charge you want to ship them with, or if it's a
Mhm.
HO refrigerant and they have these limitations on line size. There's a lot of factors these engineers go into, but they're the ones that set that standard of what normal is for their piece of equipment. So that's why we refer to them to find out what is normal. What are you, sir, calling for? Linux, you want this? And it's cool because Linux will say match your outdoor coil with this indoor coil, and
Yes.
this is what's normal. And it's cool because they have a whole list of different ranges, and others will just put it one number. It's like, hey, no matter what you have, 12 degrees is normal. And there's reasons for that, but we can go into all the engineering of that. But let's find out what the manufacturer considers normal, and we'll work within their parameters.
Yeah, absolutely. And that's going to, put us down another rabbit hole is when we get to inverter technology. There is no set parameter. It's we got to weigh it in. The engineers have figured it out in the lab, and it's weighed in, and that's what it is. So what normal is? Well, it's going to be making sure you have good airflow, and what's the refrigerant level literally weighed in with the total equivalent line length. So that
That's
is
right.
normal. But yeah, you mentioned something about our approach. We can't get below that ambient temperature unless there's a restriction. Some manufacturers would put filter dryers inside the condenser cabinet. I won't name any names, but bad place for it, as we
Yeah,
all know.
I
Bad place.
understand why they did it. It's just
Yes.
it's more difficult for us to diagnose it, trying to get in
Correct.
there with their clamps, getting the temperature. Like I appreciate the reason for doing it. I just dislike it. I as a field service person.
But where I'm going at is usually we're gonna measure that
Right.
approach for the line temperatures right there by the service valve. And if that filter dryer is pre the service valve, we could have a restricted filter dryer, and
Absolutely.
then of
That's
course
correct.
be a metering device essentially, and it would throw
And
those
you
numbers.
won't know your saturated temperature correctly either because you're having that
Correct.
pressure drop, which is more importantly a saturated temperature drop. So you could be screaming inside that system and you're checking it and you don't know where you're at really.
Right. And of course that could be, a tool thing, making sure your tools are calibrated, right?
Right.
What's normal your tools? I mean, we could talk about normal all day. I'm abnormal. I don't know about you, but I'm
Absolutely
an
abnormal.
what's
I'm
normal? Yeah.
neurodivergent.
Well, absolutely. So, you know, this, with going back to the inverter technology, and oh yes, so Dirk's put this up. This is a new. I'm going to switch gears back since he put this up. This is a new teaching tool, and we could actually fill just what you were talking about when we first started coming here. Fill this thing up with different parts, right?
See, I like
Normally, we're
that.
going to have
You can
you're going to
visually
have
see what's happening in that system.
yeah, and be able to throw this thing off on a really bad charge. Hey, let's just remove a bunch of refrigerant, and all of a sudden we have nothing but superheat, right? Or we overcharge it, and we're flooding back, and it's that evaporator coil is completely full of refrigerant, and we don't want to do that because I just watched a video of yours the other day of, open up a compressor and seeing it, copper plated and all that all that those issues that come with overcharging and washing out the oil. So
Well,
yeah.
I can say I'm a very, very visual person. I like to learn visually. I like to teach visually. I
Mhm.
think if people, I'm going to make some noises here. I think if people see stuff, they can understand it better. And some people are really good at learning stuff in just text alone. That's cool. That's not me. I have to read 5 or 6 times. If I can see a picture, it's worth a lot more. So,
Yep.
for example, the evaporator coil, we're wanting to see, hey, what is our superheated vapor? So I asked people, just 1 second. This is for a like technical reason. All right, is the glass full or what percent is it full? Like what's going on with this glass here?
Is it half empty or half full?
Well, it's definitely over half. You could say like,
Yeah.
what would you call that percentage wise? It's
Oh, I would say maybe 80-20, 80%.
see, I would call this 100% full. Like you have this much of a liquid and you have this much of a vapor, so it's entirely full, right? We have vapor, which takes up space, and we have liquid. Now, if you wanted to say how much liquid, that's a different story. So that's what I start with is like, hey, let's understand kind of what's happening here. So
That's
if
it.
I'm looking on the evaporator coil side, we know that the refrigerant's changing state, it's boiling, and we can't measure saturation because it's latent heat, it's hidden. We can't see it. Same thing in the condenser. We can't see saturation, but we can measure and see subcooling. And an evaporator coil, which is the opposite, outside inside. We have red outside, blue inside, high pressure outside, low pressure inside. So inside's opposite. So I can't see the saturation. So in the evaporator coil, I can only see or only measure my superheat. So if I know I have, let's call this 10 degrees of superheated vapor, and let's say of the TXV, so normal. Let's make it a little easier. The fixed or persistent changes. But if I say,
Yep.
hey, my TXV is supposed to keep a that much superheat, and let's put some low pressure in here so we can visualize this a little
Oh
better
yeah.
because just like you guys, I like visualization. Right. So now we can see, let's say all this blue is refrigerant boiling. It's not going to be cool. It's going to be like violent. It's boiling and changing state.
Yep.
But if I know I have this much superheated vapor and I want this much superheated vapor, even though I can't see the saturation level, I know that I'm good, have the right amount of saturation. Now, one of the issues is going to be what happens is I want this much superheated vapor, but I am I can't get it in my computer. So I'm overflowing with
Right.
my saturation. I have zero superheat. So now we know that we're getting liquid back. How much liquid we're getting back? I don't know. I don't want any liquid coming back. It's a vapor compression. It's not a liquid compression. So we don't want any liquid coming back. On the other hand, if you had that pH diagram earlier talking about where it's changing state, if I want this much superheated vapor, but I have this much superheated vapor. Well, I got way too much superheated vapor. So there's not enough refrigerant changing state. And this is why I'm doing it with a water bottle. You guys are doing it much better with your visual 3D because you can actually see where it's changing state. And this refrigerant changing state, that is the magic of it absorbing heat. That 900 for water, 970 BTUs for every pound of
Yes.
water changing state. So that refrigerant, even though it's not as powerful as water, that refrigerant changing state is the magic. And so here, I love this visual. You can see that refrigerant in there where it's boiling, it's changing state. You can visualize what's happening in that system. And so we don't want to overflow. If we overflow that with liquid, we damage the compressor. On the other hand, if we don't have enough liquid in there, then we're not absorbing the heat that we need to. We
Right.
need the right amount of liquid. And so here we go. So, all right, good. Now my superheat matches my target. I have the right amount of liquid in that system. And that's what we want. If we have too much superheated vapor, I'm not absorbing as much heat, but also I am now gaining a whole lot of superheat now coming out of the compressor. It's going to be even more superheated, and I can
Right.
have an issue of oil breakdown. And oil breakdown is not normal; it's abnormal. So we want to make sure that normal on the discharge line is below 225 to stay alive. But it's funny how the whole system, it all works together. So if we have the right amount of refrigerant in the condenser and the right amount of refrigerant over here in our evaporator coil,
Yep.
then we have a balanced charge, and then we can look at our condensing temperature over ambient to see, hey, does that also match? And then I can, just like I have condenser TD, or some people call it CTOA, or some people call it
CTOA.
condensing saturated temperature rise. Inside, I have my saturated temperature below return air, evaporator TD, or evaporator design temperature difference.
Designed.
And this is going to depend on climate and airflow.
Yes.
But the temperature this refrigerant boils has to be below the air temperature so we can absorb heat. If it's not below the air temperature, we're not absorbing heat. So
Yeah.
if it's only, say, 5 degrees below the temperature of the air, hey, heat's going to go from the air and make this boil. The problem is only 5 degrees is probably not going to move fast enough to do what we need to do. And Willis Carrier didn't just make the AC to cool, he made it to also dehumidify. So this temperature
Yes.
needs to be below the dew point temperature.
Good point.
And so that's important. So typically they design this refrigerant to boil at approximately 35 degrees lower than the return air temperature coming into it. Typical design temperature. Now, when you're in a humid climate, you may want to slow your airflow down, have better dehumidification, give more time for that air going across that evaporator coil to pull more moisture out. And that's water. So 970 BTUs condensing on that evaporator coil. That would be a normal number. And if you're in a humid climate, you may want that TD between the return air and the refrigerant to be greater. So you may be even closer to 40. In Las Vegas, you don't need any dehumidification. You want more airflow because that lower saturated temperature is just wasting energy. So you can have the saturated temperature much higher and have a less of a TD. In other words, your coil temperature is closer to your return air temperature, and because you don't need the dehumidification, so you can gain that back by sensible cooling only and be much more energy efficient. So sometimes in a very dry climate, you may only have a 30-degree design temperature difference. Humid
Right.
climate may have closer to a 40, but typical, I mean, just generally speaking, 35 degrees. The boiling saturated temperature of the refrigerant is 35 degrees below the return air. And that's a big one because people get delta T, which is two different
Yes.
mediums, confused with TD, which is two different numbers. There was, oh my gosh, you have a scholarship for the man. I can picture his face right now.
Oh yeah.
Is a brilliant man,
It'll
but
come to me in a minute.
he would argue to the death on making sure that people did not confuse temperature difference with delta temperature difference. And
Yes.
so that was a big thing. And he was Brian D. Baker, amazing
Yep,
man.
thank you.
So he would really, I used to be like, okay, I know the difference. I'm just gonna not really push that. And he held that line. I'm like, you know what? That is important to understand that temperature difference between the air and the refrigerant boiling or design of that is different than the return air temperature and supplier temperature, or refrigerant into a filter dryer, refrigerant out of a filter dryer. Normally, we don't want any temperature drop. You can allow one or two, but normal, you don't
Right.
want any temperature drop across the filter dryer. So those are what we talk about normal, and all of that works together, can affect one or the other. So I love being able to visualize that. I'm doing it with water bottles, but obviously that's not the most effective way when you're dealing with somebody remote. So how can you get them to understand this is happening? with technology, and you have
Yeah.
the actual components, so you can show live with animation what's happening, which is way better than a water bottle. I mean, this was better than
Uh,
just a whiteboard, but I love how you guys have taken a lot of these things that I do. You didn't take them. You have found a different way of presenting the same way I do visually to somebody that's learning remote. They can have this right here on their phone and they can see the stuff happening. And I think it's a very powerful way of learning. That way, when the instructors in the lab, they've gotten this theory down, they understand this. So now when they're ready to get their actual hands on, it takes both. So they've learned that theory, which some instructors struggle with. Now they can come into the lab. Hey, let's apply this. Let's
yeah,
apply this information that you learned. And now you're taking that student way ahead a whole lot faster. Now that student that missed a day of lecture, okay, they can learn that at home. Come into the
absolutely.
lab and let's utilize this lab. Let's have more lab space, less classroom space, and let's apply what they're learning. I used to complain like, well, you got to read the book to really excel in class. And nobody wanted to read. I didn't want to read either. But now with a lot of the visual aids that we have, it takes the books and puts it into pictures where we can absorb that information, relate to that information a lot faster. And I'm absolutely loving it.
Absolutely. And for the record, I make mention this often in most of our episodes, and to people who want to know more about Visual 3D Academy, and that is, we're not here to replace the instructor.
Right.
So, Ty, we're not here to replace your bottle and squeezing with food coloring. In fact, nobody could teach like you. I wish you're one of my mentors, and I wish I could teach like you. We're not here to replace the books either. Okay. And we're trying to bring all those modalities together. We all learn differently, and being able to have those different modalities to learn said topic, what's normal, what's abnormal, or it could be electrical fundamentals, it could be whatever it might be, whatever the topic might be. Everybody learns differently, and we're not replacing the instructors, the books. We're here to help instructors. We're here to help students learn the topic that this be presented to them. So, yeah, absolutely. And you know, Ty, we love transparency here, and you've kind of already sung your praises about Visual 3D Academy, and we appreciate that. I know it's genuine. You're one of my good friends and a mentor. But if you had a full-fledged development team at your disposal, and when I say full-fledged, I mean they could do anything. What would you want to see them do and have them do? Is there something that Visual 3D can do better?
Well, there's always something that can be better.
Always.
Nobody's ever perfect. A good job is never complete. It's always ongoing. I remember working. Well, I remember when Dirk had the actual the test board, the actual board, you could test it live, and then
Yes.
he put that onto a program where students could play with that at home even when I wasn't there. We only had one at the school, so we
Mhm.
everybody was fighting for it. So now everybody had access to that theory. When they came in, they could make better use of that time. And you're showing the video of the capacitor. I remember when Dirk was working on that, and it was I have to cut all these things open, which makes a huge mess. And he was making it where you could see it, and you could see all the pieces inside. And now when somebody did see something cut open, it made them really, oh, I remember seeing that. I can't show electrons flow, even though I cut it open. I can't show electrons flowing through it. I can like, oh, well, just have to imagine. And Dirk's gone like with his whole team of like, oh, let me show you how these electrons would flow between the plates. And I'm like, that's cool. And I love how the fact of you guys will ask, hey, is this okay? And I'm like, hey, no, that's great. Or I'll say, no, I don't like that. It doesn't represent it. And instead of trying to convince me to accept it, you're like, okay, let's go back and try a different way and make this that next level. And I know you can't make everybody
Right.
happy, but I appreciate you guys really are trying and figuring out that because I'm not an easy guy. Like when it comes to certain topics, I'm like, no, this is important.
Yeah.
And you guys really always bring that bar up. And there's always something more to learn, but I love how you're taking the pH diagram, which is very difficult to teach for any instructor, and you're making that laying the refrigeration cycle over it, and then you have those next steps, which I'm sure aren't ready to be released yet, but you're able to actually put all of the readings, your normal readings, in that to visualize it, and then you can change it to make it abnormal and see the difference. When I
Yeah.
repaired stuff, I did a lot of maintenance, what did installation, then maintenance, and then service. And my employers were like, hey, we want you to understand what normal is so that you understand how something isn't working right, that's abnormal, and how to get it back to what normal is. And normal is not pressures. Like I
No,
oh,
it's not.
just It does that. But understanding superheat subcooling, the design temperature difference inside, the condensing temperature over and outside,
Yep.
and delta T, and how delta T is not this magic number, how a lot of things affect it. But having all that together can be heavy. And here you guys are putting this in where it's visual and it's relatable and you can connect to it and you can change one thing and see everything else happening. So it's not just like, well, what I get people ask, well, what would happen if if this happened and that happened? I'm like, I don't know. I have to draw this out and think about it. And
Yeah.
here you have with a program, you can change those settings and wouldn't just show subcooling, it would show like the whole system, how it's changing. And that's powerful because I have to sit and think through all these process and work the math backwards to get to the answer. And you guys are doing that like right here in the computer. So I'm super excited to start doing more of the teaching with what you're building because
Yeah.
I've been playing with it. I've just been nerding out on it, just playing with all the different things and having fun. I feel like a kid again after 30 something years. Like I feel like a kid again going through these
Yeah.
processes and seeing what's happening. And it's been really cool.
And it's true with, I'll take a practical exam. When I was studying for my CMHEs and CSMEs rather, and pathway, and I'm like, I'll stop and I'll close my eyes. I'm like trying to visualize this. And of course, you can't take Visual 3D Academy in a proctored exam. But my point being is it helps you visualize it so you don't have to sit there and tattoo on the back of your eyelids or envision this completely on your own without that support. But absolutely. So yeah. So over the next several episodes, now again, this is a guided pathway, 8 episodes, and you're the one about normal because, well, who else isn't normal other than you and me, right? Wink, wink.
Well, this is ironic because I am not a normal person. So
I know.
the fact that I'm talking about normal is hilarious. The irony is off the charts.
So yeah. So we're gonna be coming back to this normal baseline. Okay, what was your DDT or design DDT? What is your approach or expected approach? Of course, it's going to be manufacturer specific, obviously, but you don't know what that is unless you know what that is. And so, what do you want the learner to carry away from today before we start changing the system? So basically, going from undercharge. Next week we'll talk about undercharge. And then week after that we'll talk about overcharge, etc. What do you want them to understand about normal before we move on to diagnostic?
Just don't be afraid of all these numbers. When we started out, I remember like the very, very first guy that I worked with, he was like, "Oh, well, what are your pressures?" And and then they were changing all the time. Like, well, he goes, "Well, that's about right for today." And I'm like, how are you supposed to ever know what it is? Well, it just feels about right. I'm like, all right, so we're driving a car with a broken speedometer. We have to feel if it's about right. And then I get to another company like, oh no, you need saturated temperatures. And with saturated temperatures, you can see that the suction temperature should be 35-ish or whatever degrees
Yeah.
below your return air. Oh, but that's way better to work with. My condensing temperature back then, well, it should be about 30 to 35 degrees below above the ambient. So as your ambient
Mhm.
temperature change, you could tell your head pressure. It's like, that's way better. And then I
Mhm.
get to another company, they're like, that's good, but you don't know how much refrigerant you have in the two components. So let's do subcooling and superheat to see how much refrigerant we have. And then once all those pieces started coming together, now I'm able to fix stuff that other people can't. And
Mhm.
understand we all have our habits that we're stuck on. But once you're understanding more of the system, it comes together and it makes
Yeah.
sense. So now instead of having gauges, right, we have all this really cool
Yes.
probes and stuff. And this is taking information and putting it on our phones. And don't be afraid of this. Right. So a whole generation, 2 generations now have grown up with this. So
Mhm.
now this is what people are used to working with. And as an older, more experienced person, it took me some time to first realize I'm going to
Yes.
let go of this analog because I don't have an analog phone or radio, or I still have some analog amp meters, but like
Yeah, you do.
everything's digital. So I finally embraced in 2020 the probes. It puts things on a phone, and now I can visually see a lot better what's happening. But still, it's just numbers. If you don't know what normal is, you have to have a starting point. And for me, as I get older, it's harder to see some things. And so now I have on a screen where I can see the numbers all in front of me real easy without having to do a whole lot of math and having to make a sheet up with all these scratch notes. So but it's still not being able to visualize it. So being able to
Yep.
teach from a point of, hey, understanding the cycle, understanding what these numbers mean, understanding where normal is, makes a technician when they get at that lab using whether it's the old school gauges or using actual probes, makes them a whole lot more effective in their diagnostics. Now, these numbers mean something. They can visualize, they can connect to it, they
Yep.
can have a more of appreciation of what's happening. And then we have better technicians. Who doesn't want better technicians?
Right. So, yeah, I mean, what the pressures, right? So, yeah, so Ty, so I want to say thank you for helping us establish the foundation of this next guided pathway, right? What's normal. So, refrigeration diagnostics does not begin with deciding what is wrong. It begins by understanding what the system should be doing under the conditions that are in front of us, and sometimes what the manufacturers recommend, right? So pressures, temperatures, superheat, subcooling, DDT, approach, they all play an important part of the system and what is normal. So learn more at visual3dacademy.com. With this episode, we begin to our refrigeration diagnostic pathway by establishing the normal operation baseline. Uh, we will use this throughout the next upcoming episodes ahead. Next week, we take the baseline and begin changing the system as we look at an undercharge condition and what those changes should tell the technician. See it, learn it, apply it. This is HVAC Visualized. See you next time. Thanks again, Ty.
Thank you.